this is the second part of the Chapter 2 lecture notes, and we're going to start with slide number 24. Let me go ahead and... All right, there we go. So on this is slide 20. Yeah, slide 23 on the previous slide, you saw a list that showed these three elements: hydrogen, helium, and lithium. And you can see here hydrogen is H, helium is He, and the symbol for lithium is Li. So, and what you're looking at are models that are in the orbital, they're the orbital models, so that you can actually see the number of electrons and where they're located. But anyway, we can tell the atomic number of hydrogen is 1 because there's 1 proton in the nucleus, and its mass number is also 1. Helium has an atomic number of 2 because the red protons, the 2 protons, there's 2 of them. So atomic number is the number of protons. So that means helium has an atomic number of 2, and it has a mass number of, you just count the subatomic particles in the nucleus, which would be 2 protons, 2 neutrons. So its mass number would be 4. And if we were to draw the symbol that you would see on the periodic table inside one of the boxes, excuse me. You would see the symbol for helium, which is big H, little e, and the atomic number is 2, and the mass number is 4. Okay, and I'm not going to draw this out for lithium, but lithium's atomic number would be 3 because it has 3 protons, and its mass number would be 7 because 3 plus 4 is 7. So definitions, atomic number is always the number of protons in the nucleus. And for every atom, just so you know, we're going to talk about different changing numbers of electrons and different or changing numbers of neutrons. The number of protons for an atom is never going to change. That's actually what defines the atom. So if you see a symbol that says an atom has 2 protons, it always does, okay? Whether it's in the form of an ion or an isotope, doesn't matter. The number of protons is always going to be the same for that atom. The mass number is the total number of protons and neutrons in the nucleus. And we talked about that already. Now, isotopes are going to be atoms of the same element, but their neutrons are different. They have the same number of protons, so they're the same atom, but they're going to have a different number of neutrons. So what that means is, so you need to know this for isotopes, they have a different number of neutrons, and since mass number is protons plus neutrons, then the mass numbers will also be different, okay? And then the atomic weight, you may see that term sometime. It's similar to the mass number, but it's going to be the average of the mass numbers of all the isotopes, and therefore you're going to see it as a decimal, okay? So hydrogen is a good example of an atom or an element that has different forms called isotopes, and you can see the different forms here. The most common form of hydrogen is called hydrogen, and it has no neutrons, so its atomic number is 1 and its mass number is 1. But the isotope of hydrogen that we call deuterium still has an atomic number of 1, but it now has a mass number of 2 because it now has, instead of 0 neutrons, it has 1 neutron. And tritium, which is another isotope of hydrogen, has an atomic number of 1 because that never changes, and then a mass number of 3 because there are 2 neutrons. Sometimes isotopes give off radiation, and so we call those radioisotopes. Radioisotopes are a valuable tool particularly in medicine. Sometimes we will administer radioisotopes, like, for example, the thyroid gland. Whenever we do a scan of the thyroid, we use radioisotopes of iodine, because the thyroid makes chemicals that contain large amounts of iodine. And if we introduce radioactive iodine, then that it will show up in a scan. We can pick that up in a scan. So we also know that when we do this kind of thing, that all radioactivity can damage living tissue. So we can use radiation to destroy cancers, but some types can actually cause cancer. Okay, let's move on to the section 2.3, combining matter or combining atoms. Molecules and compounds. Both are combinations of more than one atom. A molecule, the definition is two or more atoms bonded together. But notice it doesn't say different atoms. So it can actually be, for example, come down here, 2 atoms of hydrogen or 2 atoms of oxygen. They're molecules because it's not just one hydrogen atom or one oxygen atom, it's 2 chemically bonded together. But because they're not different, you can't call them a compound. These are the formulas, by the way. The H2 and the O2 are the formulas for hydrogen gas and oxygen gas. The oxygen gas that's in the air that we breathe is actually 2 molecules of 2 atoms of oxygen chemically bonded. So a compound is a molecule that has 2 or more different kinds of atoms. So if it's just got 2 or more of the same atom, we can only call it a molecule. If it's got different kinds of atoms, then we can call it a compound or molecule. So this is a formula that I would recommend strongly that you learn. C6H12O6 is the formula, the chemical formula for glucose, and it means that glucose contains, I'll see if I can write it for you without making a mess. Glucose is the sugar that's found in our blood. We call it blood sugar. I did just make a mess. I'm sorry. Okay, so it's Glucose, glucose, and it's got 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. And that is a formula. If I were you, I would put it in my notes and I would learn it. Now we're going to talk about mixtures. Mixtures are 2 or more components that are intermixed but not chemically combined. So we have solutions, colloids, and suspensions. A solution is like mineral water or salt water, or even if you dissolve sugar in water or dissolve sugar in your tea or your coffee, that's going to be a solution. That means you're going to have solute particles dissolved in a solvent. In this example, the solute is the minerals and the water is the solvent. Then you can have a colloid in which solute particles are larger than they are in a solution, and they scatter light, they don't settle out, so it's a homogeneous mixture is what we call it. But Jell-O is an example of a colloid. Whipped cream is an example of a colloid. So this is going to be thicker. It's not going to be a liquid. It's going to be a semi-solid normally. And a suspension is when the solute the solute particles are very large and they can settle out. So blood is an example of a suspension, because when we centrifuge blood, this is a mixture of blood before we have spun it, put it in a centrifuge machine and spun it very fast. But when we spin it, it causes the heavier particles, the blood cells, the red blood cells, to settle at the bottom. And then the liquid part, the plasma, which is still a solution, it's just the red blood cells are the part that make it a suspension. The red blood cells are suspended in the plasma. Now, plasma still has dissolved particles in it, so the plasma itself is a solution with water as the solvent. and the solutes would be things like sodium ions and there's so many nutrients such as glucose and amino acids, different things like that. So solutions are homogeneous mixtures. That means the particles are evenly distributed throughout. There is a solvent, which is usually liquid such as water, and then a solute, which is dissolved in the solvent. So an example in the human body is blood sugar. Glucose is the solute, blood sugar is glucose, and then plasma, blood plasma is the solvent. And blood plasma's, the main solvent there is water. So we should really say water is the solvent. Sorry about these lines. I'm trying to learn not to do this, but they gave us a new laptop. And my old one was a touch screen. And I naturally do not have very pretty handwriting, if you haven't figured that out. But when I do this, when I write little notes, and I don't write a whole lot, but if I feel like I need to, I haven't gotten used to it's very sensitive. So anyway, that's W-A-T-E-R, water. And it says true solutions are usually transparent, like a salt solution or sugar solution. And the ways that we express concentrations of solutions is we will say it as a percent. Like if it's a 10% salt solution, it's 10 parts salt or solute to 90 parts solvent or water. So the 10% actually represents the solute. That's important. The percent actually represents the solute, which is salt. And you can also do it like milligrams per deciliter. So a normal fasting blood glucose level, and this is interesting because I think a lot of people don't know this. You know that your blood sugar needs to be between fasting blood sugar, they like for it to be between 80 and 100, like for it to be less than 100 but not too low. So if you were to check your blood sugar and it were between 80 and 100, you would be that's considered good, and you're probably not a diabetic. I am a type 2 diabetic, and I can tell you my fasting blood glucose levels are not between 80 and 100 right now, but I'm working on it with medication and diet and exercise. But that may be more information than you want to know about me, but I try to, throw things in there. My daughter is a type 1 diabetic, so that's a little different, and you will hear me talk about her for sure throughout this course. Because it's just a good example that I happen to know about personally. But anyway, the 80 stands for milligrams of glucose per deciliter of water, or deciliter of blood plasma, which is the solvent is actually water in the blood plasma. So 80 milligrams of glucose in a deciliter of water is what that 80 means, okay? So these are two ways you can represent the concentration of solutions. Another one I'll give you an example of is normal saline. If you ever have to give someone, I'm sorry, I can't think, an IV fluids, it's 0.9% means, or 0.89 a lot of times, is the percent of saline or salt in the water. And they do that because that is the same as what's in your body fluid. So it needs to match.